I think recording has started. Hi everyone. Today we'll be talking about the how to use advanced neural network functionalities using Keras and TensorFlow and PyTorch. Let's get started. First, we'll be looking at using Keras TensorFlow for implementing high-level functionalities. You can find the GitHub repository over here. We create a sample data set. We have a base model. Then first we can how to use L1 and L2 regression. That is pretty straightforward. All we have to do is initialize a regressor like L1, L2, and then just pass it to the kernel regularization. We are comparing the performance. Dropout is basically dropping out random layers. Now to drop out a layer from the previous layer, we can use a dropout layer. Point two would determine like our node has 0.2% probability of being dropped off. Then you have early stop. Early stop is basically, let's say you have training for 50 epochs, but midway you reach a desired accuracy. In that case, you would like to stop. So you just basically have to implement a callback. Callback is basically a function or an instance that will be called at certain events during a training loop. So we are just setting it. We are training for 50 epochs, but after 25 epochs, because we reached a desired accuracy, we are stopping. So dropout is valid for training, but how to use dropout layers during inference as well. So for that we use Monte Carlo inference. So basically, we just said a training is equals to true, and then stack it. And this way we can use the Monte Carlo instance. Now initializing different techniques for initializing weights. First, you have weights are initialized with zero or constant method. So you just kernel initializer is the way you can use to initialize weights and biases. So for zero or constant, you can pass zero, or for constant, it could be any constant value. Then for uniform and normal distribution. So for that, you have the random uniform distribution and random normal distribution functionalities of Keras. This will make sure that the weights follow a uniform or random distribution. Then you have the rollout initialization method, similar way. You also have the he initialization method. You use TF TensorFlow initializer, he uniform, or he normal. There are two versions. So yeah, you have orthogonal method, the identity initialization. Here the logic will be same. Then you have custom dropout function. So for that, you have to implement a layers. Your new class has to implement a layers functionality. And yeah, it basically calls the dropout function like the parent function is dropout. So the parent class is dropout. It will basically call it and make any changes you want. Then you have custom regularization. So your own logic for regularization. So here the regularization is if you want to do 0.1 into sum of squares. So this is my regularizer. We just pass it as a regular, how we passed earlier for kernel regularizer. We pass the L1 instance, right? Here we'll just pass our own regularizer. Then you have callbacks. So this is basically different callbacks during different parts of the training cycle. These are functions which you would like to call. This is the function which you like to call on epoch, and this is another function which you like to call on epoch. And you can also have batch end, batch beginning, epoch beginning, and so on. And then you have TensorBoard, which is basically allows you to use just a second. Let me see. What's the name of the file? Neural network. This basically runs JavaScript, so I don't know. It allows you to use the history to make visualization for the model. So TensorFlow model always returns in history, so we can use that for making visualizations. It saves it in JavaScript format when you're running it locally. So I'm not sure. Yeah, in this format, you can see how this is TensorBoard for that. And then you have Keras Tuner, which basically allows you to fine tune different, like figure out different hyperparameters. Here we have dense layer, and whatever we want, we need to pass it as hp.choice. So now the dense layer will try 16 nodes, 8 nodes and 30 nodes to figure out which is the best one. That is this using TensorFlow. Now we have implemented the same using PyTorch as well. The only difference is that the logic for training the loop will become, you cannot use the model.fit method directly. You'll have to write your own training loop as you do normally with TensorFlow and with PyTorch. And because of that, a lot of callbacks can be just replaced by methods and functions. So here you have L2 regularization. So I can just see L2 lambda is 0.01, and in optimizer I will pass the sorry, yeah, we'll calculate the L2 regression value and pass it to the loss function. And similarly, we have early stop. In early stop, it is just a condition because now we have a control to the entire for loop. Then for Monte Carlo dropout, it's a similar thing. You implement a class using an input module and call the MC dropout, the Monte Carlo dropout function, the and yeah, you have the same thing for inference. So these are basically the same functionality, but with the PyTorch. So different initialization weight and different ways of initializing weights in PyTorch, and so on. Now let's look at data augmentation using Keras CV and data augmentation. Let's look at that first. So Keras CV basically allows us to use the layers architecture to make some changes to the image. So let's say this is a sample image. Now we have a layer called random rotation, which basically rotates the image. Then you have another layer called random augment. It will provide a random augmentation to the image. Then auto contrast will generate a new random augmentation to the contrast of the image. Randomly zoom in the image and share in the image. Once you run this is what you can get. Like each of the augmentation is added as a layer. You can add them in your network as well or in your pipeline to make things easier. So this is basically image data augmentation with Keras CV. Then let's look at data augmentation using Fast AI. You have an image, and then you have random transformer. Split IDX is for your input output split. Let's have an image. This is the original image. Then I want to perform some sort of random transformation on this. You want to perform some sort of flip on it. Different variations of flip. It's just a simple call with image to it. Resizing, padding, and cropping. This is how you do data augmentation with fast AI. Now, classification and data augmentation with speech. So we'll be using Ogly, which is a package by Facebook for this. So so first we just basically get an image data. We get the sound data, which we get from data/mini speech. It is so you can refer to this. I referred this notebook over here on how to build a model on audio data. We initialize a TensorFlow data set, get the spectrometer of the audio, and then build a model basically. That is the standard part where you're just building a classification model. I want you to note that train accuracy is 78 and validation accuracy is 83. This is going to be important. And now let's try some augmentation using the Ogly version. So this is basically using the AUDS part of the audio module. I can change the shift in this manner, add background noise in this manner, and then I can save the file in the folder here. Now we figured out how to apply augmentation to a single file. Now what we'll do is we'll go through the entire data source for 50 files belonging to for 50 audio files belonging to each of the class. We'll generate augmentation. We'll be adding background noise to the augmentation and saving it in those folders. Once we have the new data present in a data folder, now we can initialize the tensor data set object again, and now we can see the number of instances has increased. So earlier we had 8,000 over here, and now we have 8,400. Then basically we'll do the same thing, get rid of our dimensions with just one value, then generate the spectrometer and use the spectrometer for training. The same model we'll be using. And out of 5 epochs here, we can see that the test accuracy now is from 78. Train accuracy, we went from 78 to 88, and validation accuracy remains the same. So this increase that we are overfitting, so high chance that most of the data which we are generating is getting ended up in the train set and not the test set as well. So this is augmentation with image, sorry, with audio. The next we have tabular data. For tabular data, we'll be using this tabular data augmentation. So basically, what it is basically like you have other methods like SMOT and so on to get it done. It's basically synthetic data generation. So first we fit the entire. So you have something called a learner and a runner, DT runner. So you fit those things to your entire data. One thing is we just need to specify which are discrete values, which are columns where discrete values. So it doesn't like, let's say you after encoding your labels, you have value 0, 1, 2. So when you're generating synthetic data, you don't want the augmented data to have values of zero point 0.1 for class label. So that wouldn't make sense. We just need to specify what is the uh, sh- discrete values. I think we are doing it somewhere over here. I think we are specifying it over. This is the target. Yep. So we basically fit the model. Then you see how is the validation, how is the loss changing. So this is basically the values of this, what you call it, learning rate, finding the correct best learning rate. So we found the best learning. Through this, we find the best learning rate. And then we use that to build a model around that data. This time we're not predicting anything, but rather we are predicting the data. And then we just use a loop to generate three samples. So here when we say number of samples is equals to three, it's going to generate one sample for each of the classes. So we have three classes in the TensorFlow and this data. This data set will be generating one record for each of the class. So we run this 10 times and that would be a new fake data. And then when we compare the summary statistics of our fake data with the new data, we find that it is very similar. There are some differences for sure, but it is very minute. And then we basically combine the real and fake data and retrain the model. And this time we can see we have received a much higher accuracy. Now we do the same thing for text data. For text data, we'll be using something called NLP aug. It's basically NLP augmentation. So first, we are using semantics review and semantic data. So first, basically, we map positive and negative, find the max length, tokenize it, build a model, standards up. Now we look at augmentation, how we can use NLP aug. So there is character-based augmentation, word-based augmentation, and sentence-based augmentation. So first, let's look at the original text. Then let's do a new spelling augmentation. So here basically we substitute words with the wrong spelling. You can see the lazy is written wrong over here, then the is written and lazy is written in correct fashion. Then you have the synonym augmenter. So basically a word is replaced by a synonym. And then you have like so basically this is a chain where based on an input, sometimes I would like to apply the spelling augmentation and sometimes the synonymous augmentation. And using that, I apply augmentation to the original text training set, get new data. So I only apply to first 100 records in the training set because this was quite slow. And then you use that to build the model. And here again, you can see that the train accuracy has increased. Validation accuracy is roughly the same because we are not like increasing the data for the test set. Now for time series, classification for time series. So basically, yeah, we basically generate a synthetic time series data. Okay, first we build a base model, nothing fancy, and now we look at augmentation methods. We are adding jitter. Jitter is basically random noise to the data. Scaling is zooming in and out of the data. Then you have the random curves, so basically generating random curves in the data. Then you have generating a wrap, and then using these couple of techniques, we generate new data. And then we train again the model on the augmented data. Now for video, I was trying to use the ugly video version. So first, basically, we are using the action detection data set through which we build a simple model. We extract the frames and so on, and we build a simple classification model over here. So mod, yep. We reached the accuracy of 99.67% and so on. And you can really refer to this. This is where we figured out how to use, how to train a video model. Then when generating video augmentation for videos, what we found is after one point when we are trying to overwriting the file, trying to use compose, there is some version issue because of which we weren't able to run the video part. Now for images, it's basically the same what we did for Keras, but this time we are going to be using MNIST and just random augmentation here. And you can see the performance increase 93 compared to original, which was 90. Wait, this is how much? 93 and what is the validation accuracy? 95 and this is 98 and 96. So overall augmentation kind of decreased the performance in this case. So you'll have to look into would there be a better way of performing the augmentation or not. Then we are using TensorFlow to build a neural network where everything is done from scratch. First, we define a sample data. Then we define our own custom loss function, which is the Hoover loss function. This function is not being used. This is going to be used because it allows us to dynamically set the threshold value. Then we have our own regularizer class. This is what we saw in the first notebook. We have our own loss function, which uses the function we created above. The main thing is you are implementing. So whenever there's a custom, any version of TensorFlow, you are just basically creating a new class, which is going to be inheriting from the parent TensorFlow class. So for a regularizer, you will be inheriting from the TensorFlow regularizer class, for a loss from the TensorFlow loss class, for a metric from the TensorFlow metric, for optimizer from the TensorFlow optimizer, and so on. Now we have our own logic for customizing the like initializing weights. Our constraint, the constraint is weight should be whenever the weight should be is less than zero, the weight should be converted to zero. Then your own dropout layer, same way as I said, whenever you are implementing something, you are basically whenever you're making a custom implementation, you'll basically be inheriting the TensorFlow class, implementing then our own layer. So each layer is to have build, call, compute output shapes, get config, our cycle scheduler. So this basically allows us to change the learning rate at the end of each epoch. Our optimizer. So this is basically our implementation of Atom optimizer. And using all the custom layers, this is how we'll be using. So dense layer, 30 activation is Celu. The kernel initializer, how do we initialize the waste? This is our own function. Constraint, these are the constraints. This is the function we set for certain constraint. Regularizer, this is the regularizer we set. Like alpha dropout, this is the layer we created. Then activation, here we are using the custom activation. And when we compile the custom loss function, the custom optimizer, and the custom matrix. And using this, we train the models. And basically a screenshot of the tensor board which you saw. And now custom models, basically, other than sequential, if you want to build something from blocks, so this is where you use custom models. You have residual block, and using the residual block, you'll be creating a residual regressor. A regressor is made of multiple residual blocks. And we use that to build the custom model. And then we have custom training loop. So you have our model, okay, you compile it. And now a couple of functions to help us with the visualization and so on. We set the epoch, path size, step size, and so on. And then we go through the loop that we randomly do or create a patch. And from that patch, we use the gradient tape functionalities from TensorFlow to implement the learning. This we have covered in the base. So this loop is basically a derivative of implementing neural network from scratch using PyTorch, which we had covered in the previous video. That's it for this assignment. Thank you.